I'm going to walk through an example of using agents to retrieve information from documents. I'm going to set the agent up with two tools, one tool to search documents and the other to read specific sections from those documents. Now, let me just say a few surprising things I learned up front. First of all, I think function calling or tool calling might be over, at least temporarily, in favor of having agents write code instead. I'll describe how that works. Second of all, I think embeddings are probably less important now that we have agents. Just doing keyword search in BM25 actually has some advantages because it's more deterministic. And third of all, I found the most performant way to use agents for retrieval is to try and give them information in the same way humans would want that info. That's why I've set them up with a tool to search and a tool to read documents. Now, one interpretation of an agent is just a language model that has access to tools and can do tool calling or function calling. This is something that's been around for about maybe a year and a half now, and most language models are trained so that you can pass in functions like, say, to get the weather, and the language model will decide based on your query. You might say, what's the weather in Paris? It will decide whether either to directly answer or to invoke a tool call and use this function to get more precise information. Now, when that's done, typically the language models are trained to respond in a structured way. So they'll provide an output that is often in JSON format. And this JSON format can then be passed into your function that you want to call by running a script and sending the answer back in to the LLM. But actually, maybe all this structuring is unnecessary because you could instead, rather than having the agent actually respond with a JSON, you can have the agent just respond with some standard code, just like a coder would write. And I'll show you how this works, but this is the key insight behind SmolAgents. The idea that instead of using these tool calls, which require fine-tuning of the models and which require handling all this syntax, you can just have the language model write code and execute the code. Now, why is that a bad idea? Well, the problem is if you execute arbitrary code, you can run into problems with your computer getting damaged maliciously somehow or accidentally by calls that are being made by the code. But HuggingFace have come up with a way around that. They've created this kind of safe Python environment that only allows certain imports. And by doing that, by restricting what the code can run, you can just run simpler functions that are much less likely to cause any harm. In fact, if you really want to, you can run the functions on some separate kind of server, and there's a service that you can integrate here in SmolAgents for that. But really, even the base implementation is relatively safe because of how limiting it is on the imports that can be used. So I'm going to start off by showing you an example of how SmolAgents work. I'll run through an example I've prepared in a public repo in Basic Inference. You can find it if you go to github.com, Trellis Research, and then go to basic-inference. And you'll see there's now a folder called SmolAgents, and there's a test agent script that I'm going to run right now. So that'll help you understand how SmolAgents work. Then I'm going to expand with a much bigger example where I write up two different tools. And the tools will be, first of all, a tool to search and a tool then to actually read the documents. So I'll talk about that later, and it's important how you build the tools. So first, let's understand how the SmolAgents work. And for this, I have cloned the Basic Inference repo, and I've cd'd, changed directory into the SmolAgents branch here, and opened up test agent. So to run the agent, you can start off, I recommend using UV. So you can pip install UV if you don't have it, then UVVN to set up a virtual environment. You don't need to activate it. You can immediately just use UV to do the installations. There are a few things we need to install. SmolAgents, we want to install it with Light LLM, which allows us to use any LLM like Anthropic or OpenAI. We also need transformers. And then we can just run this script with UV, run test agent. Now you have two choices. You can find more in the docs, but two broad choices. You can either use the free API from HuggingFace, just by importing HF HuggingFace API model and setting the model equal to that. Or you could use a private model provider. Say you could use Anthropic. You will need to run export on your Anthropic API key. You could also do OpenAI or Gemini. Then you will import Light LLM model and pass in the provider name, which would be Anthropic, OpenAI, Gemini. And then you could pass in the model. Now you can use any OpenAI style API as well. So you could run one with LM Studio, And you could pass in that endpoint as well by passing in the base URL. You can find that in the docs. But I'm going to use the free API, which will default if you don't specify the model to the Qwen32B coder model. You can also specify a model like this here if you wanted to run a custom model from the hub. So with the model specified, it's really a short piece of code. You set up an agent. We're going to use a code agent. We're not going to pass any tools. We'll pass in this model. And we're going to set add base tools to false. So there's some base tools that HuggingFace allows you to just kind of one toggle turn on, which includes web search. And I'm going to set that to false for now and ask this simple question here. What's the result of 2 power 3.73? So let's run this here. And we're going to see how this agent works. Now, the agent works in 3 steps. It's first of all a thought. Then it's an action, which is written in code. And then it's an observation. And the observation is actually what the code responds with. So you can see here, the whole process starts off with me posing a question. And next, the model is actually generating a thought. And that thought kind of says what it should do. It guides what code it's going to write. So it then writes some code. And then the code is executed in the safe environment in order to get a result. And once the model gets through sufficient steps, it is required to call final answer, and final answer will stop the whole process and stop the number of iterations. Now, the agent will keep repeating these 3 steps until you get to the max number of steps, which defaults to 5. But you can also pass in a max number of steps here if you like. I think it's just max steps in lowercase. I'm going to leave it to the default of 5. Now, you're probably wondering, where is the thought? Because here's the question, and it immediately shows the code being executed. Well, if you want to see the thought, you need to increase the verbosity level. So put that up to 2. There's 3 levels, 0, 1, and 2. This is level 1 by default. If you go by level 2, let's see what that does. So we've got the question, and now you can see it actually outputs the thought, which says I will use Python to compute the result of 2 raised to the power of 3.73, and then return the final answer. So it provides the code that it wants to run within this, within these backticks. And then that code is extracted just using a regular expression, and it's run in the safe environment. And then final answer is provided right here. So this is just happening all in step 0. So just one step here for the process. Okay, so this is pretty much how small agents work. Let's now check maybe a more complicated question. Here, what is the difference in attention mechanism in Llama 1 and Llama 2? And furthermore, I'm going to provide the base tools. So I'm going to set this to true to include, I think it's DuckDuckGo by default. So now we're asking a question, and we're going to allow the agent to also search the web. And what's happening when I set this to true is actually in the background, these tools are being provided in the description. So the language model knows that when it writes code, it's able to write code that calls on those tools. So what's the difference? The thought is, to find the difference, let's perform a web search with the relevant keywords and visit the top web pages. And so it writes some code that calls the web search function with this query. And then it says, okay, print out the results that you returned from that web search, which will form the observation. So that code is executed, and these results become the observation, the 3rd step of the iterative 3-step process. So given these results here, the language model says the main difference seems to be the introduction of grouped query attention in Llama 2, but it wants more information. So it says it wants to visit one of the relevant web pages. Now, it also has got access to this visit web page tool. So this is one of the other default tools. And by passing in that URL, which is actually perfect because it's Llama 1 versus 2, it's able to now execute that code and get back something more precise. So you can see it's actually getting the full post here from Anchor's website. And now it pretty much has the answer. So it says, based on the content of this web page, it understands that the change is to move to grouped query attention instead of multi-query attention. And it's ready now, therefore, to provide the final answer, which it does. And the difference here is grouped query attention. So yeah, you can see it's pretty efficient. It used 2 different tools here, which makes sense, a general search and then a web page visit search. Now, I'll just talk about one more thing here, which is the modification of the system prompt. So if you want to start customizing the agent, you can do so in a few ways. One, the main way to do it is by passing in tools, and I'm going to go through detailed examples of that. But you can also modify the behavior of the agent. You could say it's an expert on topic X, or you could say respond very succinctly or respond very verbosely in your final answer. But if you are going to do that, be careful not to just pass in a new system prompt here, because actually the default system prompt has got important information in it. It's actually got those tools. So the reason that the LLM was able to call these two tools is because the system prompt contained it. So rather than put in a new system message, it's better to actually import the code system prompt and then tag on your answer here. So let's just tag on a quick snippet here asking the LLM to be funny. And sure, we'll run that query again. What's the difference in Llama 1 and 2? It's doing the search. Now, it may not do exactly the same thing again the second time, but turns out it does. It visits another web page, but maybe a different web page. And the final answer is, okay, it wasn't actually particularly funny in this case. Let's see if we run it like this on the simpler question. And here, yeah, it's giving the straightforward answer. So I wouldn't say in this case I'm getting too much of a funny answer. I did run it before using Anthropic. So if you uncomment this code and run it instead using Anthropic, let me quickly get an API key and I'll see if that works. Okay, I've just exported my API key. So let's run now with Anthropic and see if it gives a funny response. So it gives the answer and it says, this number is growing faster than my student debt. So that just shows you that the difference between Claude in terms of instruction following and also the Qwen coder model. I'm not actually sure if I guess there is a system prompt on the Qwen coder model. I'd have to double check, but probably it's just not as good at instruction following. So this is the framework that I'm going to use. You can see how it uses coding and this kind of safer Python interpreter rather than using function calling. And I'm going to use this now to build out a system that allows me to do retrieval. And actually my system is going to mirror kind of what we saw here on the web. The web searches, there were two functions. One was kind of a broad search like a Google search. And then there was the ability to read a web page, which is like clicking on a DuckDuckGo link and then going in to read it all. And I'm going to build an analogous system for doing search of documents. So I want to allow the LLM, the agent, to search documents and get up a list of kind of the top matches. And then I want to provide the ability to read a document. Now, a document could be long, so actually I want to allow it to read a section of a document. So let's dig into a bit more detail around how that can work. For this part of the video, I'm going to be working out of the Advanced Inference Scripts repo. You can get lifetime or now annual access if you go to trellis.com. So I've cloned that into Cursor, and this repo has got very many folders around making API calls, various citation, function calling, speed test, LoRa techniques. There's much more here. There is a relevant folder as well around doing RAG retrieval using Postgres. I'll mention that a bit later in my video because it comes relevant. But for today, we're focused on agentic RAG. So I'm going to move into this folder here. I'm in the agentic RAG folder. And we're now going to run through preparing documents so that they're ready for search and for reading by the LLM. So we'll set up those two tools and then we'll start running some pipelines, some agent pipelines. Now, the key thing for getting this all to work well is to prepare your documents in a sensible and clear way. And the framework I like to think about is doing it as a human would. I've said this already, but I'll repeat it again. My goal is to provide the agent with an experience that's the same or similar to that for a human. So if I'm doing document review, I typically might be able to do a search, say on my computer, for some keywords, find some documents with those keywords, and now I can explore a document. And usually I'll do that by going into the document, again, searching the keyword and finding a section. And when I find a keyword in a section, I like to read around it. So there are two key tools. One is I need to provide search so that the agent is able to know what documents have certain queries and maybe key snippets from it. And the second tool I need to provide is a reading tool to read a specific section if the LLM asks for that. Now, typical basic RAG just involves chunking a document, like splitting it into chunks. But one of the issues with just chunking is there's not that much context for around the chunk. So I like to do this more carefully by having chunks, but assigning to each chunk a section and a document. So each chunk will have its document title within the chunk, and it will also have the section. And the question then is, how do you convert a document like one of the ones we're going to use? So we're going to look at 4 papers, the DeepSeek V2, DeepSeek V3, the Llama paper, and the Llama 2 paper. The question is, if you have these PDFs, how do you neatly organize them into sections that can then be chunked, rather than just converting it into a big blob of text? And the way I suggest to do that is to convert it into Markdown. So I've set up a script that allows me to take in a PDF and will convert it into Markdown using PyMuPDF. And you can see here, the title is in Markdown, and then there are subsections like the abstract. You can see here, I'll talk about this later, the fact that there are some hashes being used kind of confuses the Markdown syntax. But broadly speaking, I'm able to convert this into a document that will have Markdown headings. And because there are Markdown headings, I'm able to generate a table of contents, which I'll show you right away here. So I've got this clean table of contents with a title and then each of the sections. And then because I have these sections, I'm able to create chunks within the sections. So I'll have very clean chunks that are set up with the chunk of text, the section above it, and the title for that section. And this greatly improves retrieval. Furthermore, because I have separated the document into sections, I can now set up a tool that allows the agent to query specific sections. Like the agent will be able to say, okay, give me access to this document and give me access to the acknowledgement section, and I'll provide back the full acknowledgement section, not just kind of the relevant snippets. So let's look at the Markdown conversion tool, and we'll start off by running that. By the way, you'll want to set up a virtual environment, so uvvenv. I've done it already earlier. And then, I've done uvvenv. And then also you want to do uv pip install -r requirements.txt. So I've already installed those, and now I'm ready to start with my conversions. So to do the conversions from PDFs into Markdown, put the documents within the documents folder, and then run this script here, which is convert to Markdown. So I'll just copy uv run, convert to Markdown. And it does take a little bit of time because there is processing happening in the background using PyMuPDF LLM, I think it is. So we can take a look at that script. And note that it only supports PDFs for now. I will talk about in my next video how to convert into a table of contents from text files or from docx. But for now, we're just going to focus on PDF. And essentially what it does is use this library PyMuPDF for LLM, which specifically has a tool that allows you to pass in an input PDF path and will create Markdown text. Now, this library will actually separate each page. So it will use this separator here, which is 5 dashes to separate the pages. That can be useful because you can get page numbers, but I don't want it, so I'm stripping this. So it means when I get the Markdown format, I don't want any page separators. I just want the clean text. I want the sections, and then I'm going to chunk the text within those sections. So you can see here, we're just about to finish converting to Markdown each of these PDF files. And my next step is to create a table of contents. And my idea here behind having the table of contents is that when I do a search, or when the agent does a search for some keywords like Llama 2 paper, it's going to return the key snippets, but I'm going to always return the table of contents. And by doing that, I'm giving the agent knowledge of what else is in the document so that it can optionally then decide to read one of those sections in detail. Now, this will make more and more sense as you keep seeing the examples, so I'll keep moving through it. So my next script I want to run is to create a table of contents. And for that, I'm going to run uv run generate TOC. This generates very fast. And all it does is it searches for any headings. It just searches for headings within the Markdown file. And based on those headings, it creates a table of contents. Now, if you do that naively, you will get a few false flags because, as I showed you in the Markdown file, sometimes there are hashes or pound symbols, as you say in the US, and those kind of spurious hashes that are not actually Markdown headings can cause the table of contents creation to think there's a heading. So I impose a requirement that I only look at 2 hashes or more, which is like second level headings, third level, etc. I don't look at first level because that's usually the document title. As you can see here in the outputs, if I look at the Markdown, the document title is 2, so I do want that, and then I want 3. But the way that the Markdown conversion seems to work is it often doesn't provide the single pound as being a relevant heading. And if it is, it would be the document title, so that would be fine to omit it anyway, because I have the document title. So yeah, I'm just saying, if there are spurious pound symbols, one enforcing check I make is that the text that follows afterwards needs to have at least 5 characters. Otherwise, I will just ignore it. And I'm not saying this will be perfect, and it probably doesn't need to be perfect, but it'll give fairly clean tables of contents, as you can see here, for these documents. Let's quickly check the other 2 ones, see if there's any errors here. Yeah, this is all pretty clean. This one here is also pretty clean. So yeah. And the key thing is that it be clean, because these are the delineations that will be used for finding text that's in that section 6. Basically, any text that's between these 2 headings will be considered the text of section 6. So now we're at a point where we have documents that are clean in Markdown format, and we have table of contents. So what I'm going to do now is set up my 2 tools. The first tool I'm going to set up is a BM25 retriever. It's a search retriever. And the second one I'm going to set up is a section reader. So for the first one, I need to chunk each of the sections. I need to put each of the sections into a table or a database, and then allow a search to be done to find the closest chunks. And then the second tool, I'm just going to require a table or database that has got the sections, and then I'll retrieve the sections based on the titles of those sections. So let's go through the BM25 retriever first. So for this, there are 2 steps. First of all, this database or table needs to be set up. The search statistics need to be created, and that will be done by running this script here, and optionally passing in the flag refresh if you've changed your Markdown documents and want to refresh the table and statistics. And then we'll go through a tool that will allow me to make queries using that table of chunks and statistics. Now, first, a few broad comments. Why use BM25 and why not use embeddings? You absolutely could use embeddings. You could use a combination, some hybrid search. But actually, embeddings are less important, I think, with agentic search, because it's not a human writing the query. Normally, if you're doing RAG, the human writes a question and you use that query in order to find relevant documents. And the human might not be good at writing the query specifically, so it works well with BM25. And yeah, by the way, it works well. Ideal if you're doing a BM25 search, it's a keyword type search. It's going to miss things like misspellings. It's going to miss things like alternative words. Like if you say substitute, it may not find the word replacement, for example. But if you tell the agent that it's a BM25 search and it knows that, it's going to know that it needs to provide a query that is well suited to BM25. And so it's more likely to provide alternative words. So basically the drawbacks of BM25 are reduced when you're using an agent compared to embeddings, because the benefit of embeddings is that they tend to be more coarse. They allow you to semantically search. Furthermore, BM25, because it's an exact match type approach, although it's case insensitive if you normalize for upper or lower case, which I do, because it's more exact, it allows the LLM to run more precise searches. If you run an embedding search for a word like jumped over the star, it's not necessarily going to pull up all of the exact matches. It may well, because they're going to be well aligned with the embeddings, but it won't for sure pull it up. Whereas a BM25 is much more likely to pull up for sure any exact matches. And this allows the LLM to do precise searches. So actually providing BM25 is in some ways more advantageous if in this case, because it just allows that specific querying. And by the way, this is a benefit too when humans do search on documents. It's nice to be able to do keyword search because you know exactly that you're searching for this keyword. It's either there or it's not. Okay, so I'm going to run BM25. The summary of all of what I said is that you can run with embeddings too. I think it's less important because the agent knows that it's BM25 and will be able to adapt. So let's set up the BM25 database, and we're going to save it here as a pickle file, and then we'll load it as a pickle file. The pickle file will have the embeddings in it. if you want to do this, it's going to be fairly fast because I don't have that many documents. If you want it to be really fast at scale, you should consider doing this in Postgres. You could also use a third-party database. I talk a lot about the pros and cons of that in a video on Postgres RAG. It's actually in the RAG folder here in this repo. But basically, if you run your own Postgres instance, you don't lose the time it takes to call an external database. And that ends up being a significant portion of the time. So I would highly recommend looking at Postgres, especially because it's open source and free, and you can do vector type search, which is very fast. Okay, but for now, I'm going to do it just saving the database and stats as a pickle file, which keeps things easy. So let's go through a few parts of this script. What I'm going to do is take each of the documents and split it into sections. How do I split by sections? I split in the same way I created a table of contents, just by searching for these pound symbols. And notice that when I split into sections, I exclude the title, the section title, from being within the text I want to chunk, because I just take out that section title as kind of a piece of metadata and then include it at the top of every single chunk. So yeah, this is how I split a piece of content into sections. Now, when I have that content for a given section, I need to split it into chunks. And the common chunking approach here is, well, you can naively just chunk by number of characters. You can add in some overlap. You can potentially chunk based on a period, like a full stop. But my favorite way is to chunk based on complete sentences. It means you don't break the chunks in the middle of sentences. And the way to do that is to use something like NLTK and to tokenize it according to sentences. This means it splits text into separate clean sentences so that you can use them contiguously and get clean chunks. And you'll see later all the results are very clean because of that. In terms of text cleaning, this is important because if you search for a query like Paris with a capital P, you also want to find all the words Paris with a lowercase p. So it's beneficial to turn that into lowercase. And also you can basically do some simple punctuation cleaning as well. Now, technically you can improve performance further by doing what's called stemming. It reduces every word down to its stem. You can do that again with NLTK. I left it out here and it'll perform okay anyway, especially because we're using an agent, but that's something you could consider for improving performance as well. So next I define a document class that I'm going to use for doing this retrieval, and it's going to have a few attributes. It's going to have chunk content, so each of the chunks text. It's going to have some metadata. It's going to have some clean terms, some term frequencies, and then the document length. Now, these are the three statistics that are needed for doing BM25, which is not just pure keyword, it's actually related to the inverse frequency of the keywords. Basically, it will favor documents that have got similar words to the query, but where those words are quite rare. Obviously, if the query has the word the, it's not very useful to know that other documents have got the word the, because the word the is going to be everywhere. But if the query has got the word pyramid, that's probably going to be pretty rare across documents. And so if there's a document with the word pyramid, you should really emphasize that. That's a very loose description of how BM25 works. There's also a normalization for the length of the documents. So you need to pre-compute the terms, which is literally the words, the frequency of those terms in the documents, and then the length of the documents. And by pre-computing these and saving them, you have a very fast search when you need to run BM25 search. Okay, there's also some other functions here within the document class, just for pre-computing the clean terms and the term frequency. So the way this script is going to work is we're going to load the retriever file, the pickled file, if it already exists. If it doesn't, we're going to create it. And if we're running in refresh mode, we're going to recreate that file. And here we're just populating the data. So the metadata I mentioned above is going to have the file name, and it's also going to have the section title. And that's what will allow me, when I create each chunk, to put in the section title and to put in the section name. So moving on here, you can see that the way I create the chunks is by getting section data, then splitting the text into chunks, then calculating the term document frequency, and then adding the chunk into the database. Now notice how when I split the chunks here, I actually pass in the section title and section content and the metadata. And this is needed because, as I said, I want to set up the chunks to include the document title and the section title as well. Okay, so that pretty much describes how I set up the database. There's also a portion of the code here that then runs a query So you can run a query by running query BM25 retriever and then the query. And you can also run it in test mode, which just truncates the middle of the chunks to make them shorter for display on your screen. And when you're running a query, you actually calculate the score, which is the relevance of each chunk to the document. This is how the formula works here. And it will then return the highest scoring documents, the top K number of those. And later we're going to let the agent decide how many chunks to return, up to a maximum of 5. You don't want it to be unlimited in case the agent asks for tons. And when the results are returned, the way we'll format it is we'll organize the chunks by document. So we'll take the most relevant chunks for a given document. Then we'll move on to the next document if there are relevant chunks within those top 5. And we'll see this printed out. It's best to see it when we run the script. All right, a quick break there for some sports, but I'm back and going to run this script. So when I run the script, it's going to set up the retrieval, the pickle file. It'll set up the stats, but it's also going to run a query. So let's go to the README and grab the command to run the query. The query I'm going to run here, which will be querying the 4 documents, Llama 2, DeepSeek 2, and DeepSeek 3. The query is going to be, what's the title of the paper? And I'll pass the refresh flag as well, which should refresh the statistics. You want to do that if you're going to add documents or anything. So the query is run, and we will look at the results just so you can see what's been printed out. Note that I'm using, I think, top 3. So maybe it's top 5. So it's going to show multiple snippets. And it split my document into 356 sections, and then each section, rather this is actually chunks, I think. Maybe that's not quite right. I think there's 356 chunks among all the documents. And the first document that it's returning a snippet from is DeepSeek. And notice how before I even return the snippets, I return a table of contents. So for each document, I give the full table of contents. This will be useful later because it lets the agent know what else is in the document that it could query. And now here's the first snippet. So we have one relevant snippet here. And we have the score as well. I like including the score because it gives extra context on which snippets are actually relevant. And I tell the agent it's BM25, so it knows what that score means. The next snippet here, so we have a second snippet. So there's 2 snippets in that document. I said before I grouped them by document. Next, it's finding snippets from the Llama paper here. Again, I start by providing the table of contents, and then I provide a relevant snippet, a second relevant snippet, a third relevant snippet. So that's the 5 snippets. It basically found 2 in the first document and then 3 in the next one. Now, actually, the first document, I think, is a DeepSeek document, which you might think is a bit curious because my query was about Llama. But yeah, the DeepSeek document references the Llama paper pretty strongly. So that's why it's finding reference snippets right there. So that's the implementation. And this is the script, as I said, that sets up the retrieval file, the statistics, but you can also run it directly to run a test query. Now, to use any tool with small agents, you need to format the tool in a certain way. And for that, I need a separate script. So when I have the statistics and chunks set up, I need a script that follows the syntax. And you can find the guidance for this. I'll put a link to it in the video description below. But you can find it under small agents and then tools in-depth guide. And you'll see in the tool here, I'm defining, first of all, a class for documents because I'll need to import documents. And then I'm defining the tool. And the tool has got a few fields. It's got a name. It's got a description. And notice here how I'm describing exactly how this works. I'm also telling the model how to query. Queries work best with simple direct language that matches the document text. So I'm helping it to know the form of query it should use. Then I'm providing the inputs. So it needs to provide a query, and it also needs to specify a number of snippets it would like returned. And notice how I've set a max of 5, so it doesn't pick a crazy number of snippets by accident. Then the output type is defined. And then the initialization of this tool is defined. And you can define functions within it. So I have a function to retrieve the state, which will include the chunks and the statistics. And then you must have a forward method. This is the method that's run when you call the tool or when the agent calls the tool. And as I described above, it takes in a string for the query and it takes in an integer, an int, for the number of snippets. And what it does with those is a BM25 score search using the query on the documents. And it's just going to return num snippets, number of snippets. This here is the logic then to sort the results according to document. And this is the logic here to print it out in a neat way so that each of the snippets for a given document, they're included within that kind of document framework that includes the table of contents. Then I've got a function here for BM25 score. This is the mathematics of how to calculate BM25. It's actually repeated in the script I showed you before earlier, but I do need to include it in the tool. And yeah, the function returns sorted list of the doc scores. Notice we also have a method here for cleaning the text that matches the method I described earlier. Probably this is duplication. I could import it instead. So if you want to just run a quick test on this, you can comment out the example usage and then UV run query BM25 tool.py, and it's going to do a search here and return how many snippets will it return by default. I think it's probably defaulting to 5. Let's just check that. It looks like it's defaulting to 5, and probably it has returned 5, which will be more or less what I showed you already. It's a slightly different query, so different snippets that will come back. You can see here the first document, 1 snippet, 2 snippet, 3 snippets, and the second document, 1 snippet, 2 snippet. No, just 1 snippet, and the third document, 1 snippet. So it actually shows 3 documents in this case, 3 from the first, then 1, then 1. So this is working now. We have a tool, and the tool allows the agent to retrieve snippets. When it retrieves the snippets, it also gets the benefit of the table of contents of the documents from which it is retrieving. And this is already quite powerful, and we can actually take it and use it within a small agent. So before I talk about the second tool, let's implement the first tool in a simple code agent. And I've set that up here. It looks very much like the example I showed at the start of this video. The main difference, well, there are 2 differences, but the main difference is that I've now included extra tools. I said, let's start by looking just at the section tool. So we'll only include that one. We'll only include the BM25 tool. And in order to include it, I need to import it. So I've set the BM25 tool as BM25 retriever tool, and that is being imported from the query BM25 tool script. So basically, you need a tool script, and then you need to import that tool, which is defined here, BM25 retrieval tool. You need to import it into your script here. And with that, you can pass it into the tools, and everything else I've pretty much left the same. Now, I am using a few different LLMs. I recommend using Claude. It's the one that performs the most consistently. Actually, I'm going to use that for now, and I'm not going to pass in a system prompt. I noticed when I used Gemini Flash 2.0, the tool, the agent has a tendency to make traditional function calls and return JSON sometimes. And so to help avoid that, I do provide this optional custom system prompt that says to write code directly and do not make tool calls. But Claude actually instruction follows very well, so I can just comment that out. So with that, I can run my code agent using my BM25 tool. And the question I'm going to ask here is, what is the difference between the attention mechanism used in the first and second Llama paper and in the 2 DeepSeek papers? So it basically needs to find information on all 4 papers and return some type of response. So I'm just going to run here with UV run code agent.py. And you can see the question I'm asking, and okay, it's moving, it's answering pretty quickly. Let's see if we can just go up and analyze each of the steps. So the very first step here, what's the difference? And the thought is I need to search for information about the attention mechanisms. Makes sense. Let me break them down. And here's the code. So it's doing a search for Llama 1. So it's just going to search for the Llama 1 results, and that's executed. And it asks for 3 snippets. So those 3 snippets are returned. And it takes in those snippets then in the next thought and says, let's find out about Llama 2 and get information about DeepSeek. So now it does a search for Llama 2. It actually, it doesn't do DeepSeek right there, does it? No, it focuses on Llama 2 and it gets some information on that. Again, the retrieval actually pulls up some information on DeepSeek because DeepSeek references Llama 2. Now it actually kind of provides the answer in the DeepSeek paper. But we get back the snippets, and then it says, let me search specifically for DeepSeek, which again, this makes sense. And it's looking for only 2 snippets now. So it gets 2 snippets. And based on the results, it can now provide an answer. So it's taken 4 steps because it's a zero-based counting. And then it provides the answer, the final answer, and it prints out, Llama 1 is multi-head attention. Llama 2 is grouped query attention. And then in DeepSeek, they both use, the first one uses multi-head attention and the next one uses multi-head latent attention. So this is quite a good answer. And you can see how the model or the agent is able to make multiple queries to get the data it needs when it didn't get it on the first few requests. Actually, it didn't even try to get it all in the first few requests. It got iteratively the information that it needed. So 24,000 tokens used and output tokens 786. So you can see that this performs well already, just in terms of using a retriever. And I'll note that the choice of model makes a difference. If you decide to use, let's actually just do it. Let's now use the Google approach. So I'll swap in the Flash model. I tried the thinking model, by the way, but it has issues because it tends to get mixed up in providing clean code syntax and there's thinking tokens mixed in. So that's something I'll potentially look at later. But let's test this out, and we'll do it without providing this helper prompt, just so I can show you the kind of issues you run into. This is an experimental model, by the way. It's free on the API currently. So here in the first step, this is it's really the second step. And it's actually calling multiple requests at once. So you can see it's searching now for Llama 1, and it's also searching for DeepSeek. So, makes sense. It's parallelizing some of the requests, which is nice to see. Get some more information. And then it states it's pretty much got the right information that it needs. So it goes ahead to give the answer. And actually in the DeepSeek papers, V2 and 3, I don't think DeepSeek 2 uses latent attention. So it actually hasn't got quite the right information on the second paper, but it has got the right information on the third paper. So not completely foolproof here in this case. Also, you can see this does work here, but just from my other queries earlier on, sometimes I find that the model actually fails to properly function call with Gemini Flash. And for that reason, I put in this specific helper prompt that tries to force it not to make tool calls and to instead to use code. So this is the quick demo here, just with a retriever tool. The next tool I'm going to build is a section reading tool. And quite simply, I build a database, pickle file that is going to have, for each document, the sections saved separately. And the language model or the agent is going to be able to request to read one of the specific sections. And I'll show you the script for that now. So I'll go to the section reading tool. And before setting up the reading tool, I need to set up that database or pickle file that has the sections. So I'll quickly take a look at this. I'm going to instantiate a retriever. And I'm actually going to use BM25. So if the agent wants to find a document in section, the agent will specify the document name and the section name. And then I'll use BM25 search on the document name to find the closest document, and then the same within that document to find the closest section. I actually tested out using Levenstein distance, and it was very not robust. Probably just using keyword is not too bad, but BM25 I think performed the best and seems to get me the right document. So here the retriever is a little bit, it's quite similar because we're using BM25. All of the BM25 here in terms of computing frequencies looks the same. The scoring function is a BM25 one, so it's pretty much the same. And you can see there are 2 different functions here. One for finding the closest document, which just runs BM25 on the document. And then one for finding the closest section, which just runs BM25 on the section name. There's a function here then to split the document into sections. So we're just looking at where the Markdown headings are, and we're taking all of the text as the section. And that's pretty much what it's doing here. It's just finding those Markdown headings, and then it's using those in order to pull out text between the headings and defining that as the section content. Now I've got a function for loading sections. This is taking a Markdown file and then using the Markdown file to create a set of sections. I have a function to save that as a retriever. It's saving it as a pickle file, and then I have a function to reload the pickle file. So you can run this once, and if you change the documents, you then need to run it again using refresh in order to refresh the database that you're going to create. Furthermore, not furthermore, you're just going to need to run this. I'll run it now. UV run section retriever.py. And yeah, I've already created it, so the retriever straight is ready. But if I want, I can add refresh. And now it's saved 60 sections. So there are indeed 60 different sections that all these documents are broken into. Now that the retriever is defined, I can create a section reading tool. And this is the tool that's going to find the sections based on the names of the documents and the names of the sections. So yeah, it's as described here. I'm making this very transparent to the agent, finds the closest matching document based on BM25, and retrieves the full text of the most relevant section. I can say also based on BM25. And it returns the complete document title, the section title, and then the section content. I'm making clear how it's an advantage in certain cases for the agent to use this if it wants to comprehensively read a section rather than just read some small snippets. Again, I have to follow the small agent rather syntax. So I have to define the inputs. The input should be a document title, a section title, and the output is a string, which is the concatenation of the document title, section title, and content. Again, I have to initialize this section reading tool, provide a function for reading the table of contents. I also do that. So when I retrieve a section, I also provide the table of contents for that section, because this allows the agent to see if it maybe wants to read another section thereafter. The forward method is quite simple. It just finds the closest document using the BM25 retriever, and then it finds the closest section. And again, if I want to run this as a test, I can do so by uncommenting and then UV run section reading tool.py. And so here it's looking for a section in the Llama open and efficient paper, and it's looking for the introduction section. So we can see here the section return is indeed the introduction. So it looks like this tool is working well. So I'll comment that out, and now I can use this document retrieval tool or section retrieval tool within my code agent. So I'm going to define a section tool, and for that I need to import it like this. I also need to import my document section class. This is going to be used when the tool is being passed into the system prompt, I believe. So even though it looks like it's grayed out here, it actually is required. And let's use Sonnet because that's the highest performing I've found. And let's comment in the section tool. So we'll allow the language model to use either of these tools. Now, in this case, I'm going to ask a slightly different question. So I'm going to ask, give me a summary of the pre-training of DeepSeek V2. And what I expect the agent to do is to first do a general search for snippets so that it learns more about the relevant documents. And then it should decide to read one of the sections of the document. So I'll save that, and now UV run code agent.py. Just have to click save, and we can now run. Okay, so give me a summary of the pre-training of DeepSeek. And the first thing it does, it's moving quickly. The first thing it does is a search, I believe. I'll help search for information about DeepSeek's pre-training process. Let me search for relevant information about the pre-training using BM25. So it looks for 5 snippets around DeepSeek V2 pre-training methodology. It gets those snippets back. And then it says, let me analyze the retrieved information to get more specific details. And the thought is, let me search specifically for sections about the pre-training details. And so now it uses the section reader and it looks in the DeepSeek V2 document and the pre-training section. And when that's executed, indeed, it gets back the table of contents and then the pre-training section. So this is exactly what you would like. And because it gets that information back, it's now able to prepare a final answer, which it does. And that final answer, I think, is returned. And yes, indeed, that answer is returned. We can see it printed out here. It's telling us about the data, the architecture, training config, efficiency. So yeah, this has worked really well. It would be difficult to do this if I just had snippet-based retrieval, because I would be getting small snippets of the pre-training section. Whereas by allowing the LLM to read a section, it's able to be much more comprehensive. And you can see how Claude is strong enough in order to kind of mix the tools and generate a good experience for creating those answers. Let's just try quickly one more test, this time using Gemini Flash. So I'll run the exact same thing. We'll see if it's able to stay on track. So give me a summary of the pre-training. And the LLM's thought is, yeah, I need to find information. I'll start by using BM25 retriever, but it's actually, there's a small syntax error here. This is not how it's supposed to provide code according to SmolLM. So it's actually supposed to return it within code blocks, by the way. But there's an issue here. So I'm going to have to probably stop this. Let's see if it tried again. Yeah, it's failed again. It's failed again. We'll see if it recovers. I don't think it will, but it's going to stop automatically because it will reach the max steps of 5. Yeah, so here it's just failed. And what I found just by messing around, and this is why I would say to use Claude, is that if you put in this modified prompt just to force it not to make tool calls, this may help. It may or may not, by the way. I haven't tested this exact prompt, but let's see if we can do it better. Okay, so it looks like we did better this time because I've actually gotten a call. So here it's using the BM25 retriever on 5 snippets. It's got 5 snippets and it's now going to, okay, the search provides some information. It's scattered across sections. I'll use the section reader to extract the complete pre-training section. So it requests the document and the pre-training section. And yeah, this is pretty optimistic. I have the complete pre-training section. Now I need to summarize. So it summarizes. And indeed, it's providing out a different summary, but it is a summary of what we're asking for here on DeepSeek V2. So this is pretty much coming to the end of the tutorial. I've explained how to create tools using the small agent approach. I've explained specifically a tool on BM25 retrieval and why that might actually be sufficient. You may not need to even think about embeddings. If you want to improve performance, you should think about taking a look at the Postgres RAG video I created. There's a whole folder for implementing that type of approach here. I also explained how to allow the LLM to read a document. This is very much how a human would approach the problem, and I think works well for LLMs too. And when you combine these two, I think you do get a more robust retrieval system than you would without relying on some kind of agentic approach, provided you use an agent that's good at doing instruction following. Now, I will plan on doing a follow-up. One of the drawbacks to the section reading that I've done here is that the context now does get quite long. So you can see for that last question, perhaps I can scroll up. We used 21,000 input tokens. It's actually not too bad. That section I asked for is not that long, but you can imagine if you're doing inconsistency checking, pretty quickly as the LLM reads more and more sections, that's all being added into the context, and there's no active management of the context to keep it at a reasonable size. So that's something we're going to have to think about later when we go to more complex queries with agents. But for now, hopefully this shows you some of the tips and some of the learnings I've had around using agents for retrieval. Let me know your questions as usual down below in the comments. Cheers, folks.